Hello students, welcome back. Let us now go ahead and establish the fundamental theorem of arithmetic. Remember the definition of the prime number and the prime factorization lemma, which ensured the existence of the prime factorization. Do you also remember there are infinitely many primes? And finally, Euclid lemma. We went through the most general version and then the special version when the device prime, and then finally the most specific version where the divisor is prime and the dividend is a product of primes. We're going to use the third version in the proof of the fundamental theorem. Okay, so much for the preparation. Here's the statement. Every integer greater than 1 can be written uniquely as a product of primes. The existence is done. The key here is the uniqueness. So here, each pi is a distinct prime, and the expression, those are all unique. So given n, the same n cannot be written as a product of different primes with different powers. This is one way to express, and here is an alternative expression which is going to be a little bit more convenient in the technical proof. It looks a bit intimidating, but don't be intimidated too much. It may look like an infinite product expression, but in reality it is just a finite product. Let P1, P2, P3, P4, and so on be the sequence of all prime numbers in the increasing order. So 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. And then we can express any positive integer uniquely as a product of primes where the powers are whole numbers. So 0, 1, 2, 3, and so on. Now, except for finitely many exceptions, the ni value should be 0. If not, you're going to multiply infinitely many prime powers of non-trivial power, which is greater than 1, so we're going to get an infinity. So even though this may look like an infinite product, actually it's a finite product. Here's an example. For example, how can I factor 1210 through prime factorization? Here's one way. 2 to the first power and 5 to the first power and then 11 to the second power. That's one way to do it. 2 to the first power and then 3 to the 0 power and then 5 to the first power, 7 to the 0 power, 11 to the second power, and then all these, from this point on, they're all 0 powers. So what do you get? It's the same thing. It may look like an infinite product expression, but in reality, it's just finite product. Now, does this look a little bit better now? The key point here is to prove that this sequence, n1, n2, n3, that sequence is unique, so that you get only one possible product expression. Also, if you express like this, then you can start from 1. Not greater than 1, but you can start from 1, because when n equals to 1, the base case, I can simply set all the power as 0. So 1 times 1 times 1, well, a bunch of 1's multiply, so we have to have 1. Now, the key point of the fundamental theorem is the uniqueness. Let's prove the uniqueness for this base case as well. Suppose that there's another factorization, another sequence, different from all 0, so there got to be a positive power somewhere, nj somewhere. And then what are we going to do? I'll take this pj to the nj power out, and what's left is going to be the product of the other primes. And then let's make this observation. The Sanjay part stay the same, and I'll just reduce its ni power into 0 power. Alright, the whole number power into 0 power. So this thing got either smaller or less than or equal to. At the very least, we have the same inequality. So what do you have? Well, we have a bunch of 0 power, so this is all 1s. So pj to the nj power, that's what I get. But then again, that's strictly greater than 1 because that's a prime number and the power is greater than 0. So 1 is equal to this, and that's greater than or equal to that, and which is strictly greater than 1. So in conclusion, 1 is strictly greater than itself. That's a contradiction. It cannot happen. So we proved the base case. When n equals to 1, we proved it. Key point was uniqueness. Now, when k is less than n, we're going to use the inductive hypothesis for the strong induction. So any k less than n, and as a matter of fact, greater than 0 and less than n, I should have said, starting from 1, which is the base case which we just proved. We have a unique sequence, k1, k2, k3, and so on, which form the power, which are all whole numbers, so that k can be written as the prime factorization of this infinite product form. Now we have to prove for n. And the existence is easy. We already did it. But let's redo that briefly using the infinite product expression. So this is just a reproduction of 1.2, but using the infinite product expression. If n is already a prime, then by itself it's a prime factorization, or you can rewrite it as a product of all primes. So for pj, it's 1 power, everything else 0 power, so just a bunch of 1s. If n is composite, then we can rewrite it as a times b, where a and b are both greater than 1 and less than n. So they fit into this inductive hypothesis. As a matter of fact, I should have said greater than 0 and less than n, but I don't think that's really necessary. So we can write it as a product of primes like this, as a primes like this, combine those together, we have product of primes. That's it. So we have product of primes in infinite product form. But you don't have to do it this way. You already did it in 1.2 using finite product expression. Now let's go to uniqueness. In the uniqueness, this infinite product expression will be a little bit more useful. Let's use the proof by contradiction. Suppose that there are two prime factorization expressions. Oh no, this is not a proof by contradiction. Sorry about that. This is direct proof. Suppose that there are two prime factorization expressions, and we aim to prove they're the same. So the sequence of powers are identical. So we are not assuming these are different and then trying to get a contradiction. We just begin with two prime factorization, and we are trying to prove the sequence of those powers are the same. So this is not a proof by contradiction. This is direct proof. Okay, how do you prove those? Well, let's make this observation. N is finite. So even though these are all infinite product expressions of infinite many primes, but in reality, those are actually finite products because except for the finite many exceptions, all the powers should be 0, so we have a bunch of 1s only. So we can reduce both of those into finite products. We have finite products of primes so that we are ready to use Euclid lemma. You see, finite product of primes. Okay, all right, we're up to here. And then let's choose a prime factor pj of the first prime factorization. There got to be some nj that's greater than 0 because n is greater than 1. If they're all 0, I'm going to get n equals to 1. And then I'm going to factor that out. pj times what's left. So we got 1 pj here. And then the rest. And then here, the rest. Look at this ni bar. If I and j are different, then that has nothing to do with this factorization of pj. So stay the same as original ni, that's a whole number. Now for j, we have nj minus 1 because I took 1 away. And because this nj is greater than 0, this nj minus 1 is greater than or equal to 0, and that belongs to a whole number. All right? That's greater than 0. That means greater than or equal to 1. This minus 1 is greater than or equal to 0. All right. Now, let's do something similar to the second factorization. Let's take the factor pj out. pj divides n, so pj divides the factorization, the second factorization. So pj is equal to one of those factors here by Euclid's lemma. This version of Euclid's lemma, special case of Euclid's lemma, we just use that. pj divides the second expression of prime factorization, so we have equality. So that means pj belongs to one of those. So mj is greater than 0 because pj is there, and then I can factor pj out, and then here's the rest. Now, we're to compare this red and that red. This came from ni, and then ni bar by adjusting 1, and this came from mi, and then I took mi bar by adjusting 1, the jth one. And then these two are the same, of course, so let's consider n over pj. You see, n over pj, I divided pj away, divided this pj away. Are they all in the same viewing window? Barely, but they are. Divide away, so we have n over pj. And what's left is this red, and then this red. They're the same. And this thing is less than m. So by inductive hypothesis, the uniqueness applies, and therefore we have the same sequence. Ni bar and mi bar are the same. And then they made the same adjustment at jth. So original ni and mi are the same as well. This one here, this simplification, which I just highlighted in purple, that's where we use the inductive hypothesis. This inductive hypothesis. For k less than n, we have the uniqueness. That's what we used. And then readjusting, we get the desired uniqueness. So that was the final step. Okay, all right, that completes the proof of the fundamental theorem. And what do you think? You think you can produce this out of nowhere from the scratch? Even I can't do that. But you have to remember the result and some idea how they are related to Euclid's lemma, up to that point at least.